We'll conclude Module 8 with some observations about the roles of metals in various biological macromolecules. Our learning goals in this video include the various functions that metals can perform in cellular processes, as well as the role of enzymes and how metals can enhance that role. So let's get started. What are some of the critical roles of metals? Now, I'm going to talk mostly about the role of metals in humans, but of course they play a role in many kinds of living things. First of all, they can regulate fluids. Sodium and potassium are examples of this, and they must be present in our bodies in roughly equal amounts. They also provide structural support. For example, in our bones we have calcium. They provide transport of essential nutrients. This is a role that iron plays, and we'll talk more about that a little later in this video. They also can accelerate chemical reactions, and this includes metals like copper, iron, zinc, and magnesium, which play a role in various metalloproteins that form enzymes. They also are involved in tissue repair and immune function and healing, and magnesium and zinc are particularly notable in this regard. So we can see that these transition metals are really critical for a number of essential processes that maintain our health and keep us feeling good. So let's start with enzyme catalysis. I want to focus on enzymes as one of these primary functions. Catalysts are basically molecules that facilitate a reaction. They can accelerate it also, and a key element of catalysts is they aren't used up in the reaction. As much catalyst remains at the end of the reaction as started at the beginning. A substrate is a molecule whose reaction is facilitated by this enzyme. So it is the part that you want to undergo a certain kind of reaction. The active site is the location on the enzyme where the substrate can bind itself and where the chemical transformation can happen that's facilitated by that enzyme. So here is a cartoon that sort of illustrates this process. The substrate in this case is that green thing at the beginning on the upper left, and it attaches itself to the enzyme, which is the large gray blob at the bottom of these pictures. And once it attaches itself, both the substrate, the green part, and the protein sort of modify a little bit their shape so that they have an optimal fit. Once they have completely bound together, then chemical transformation takes place while the substrate is located there on the enzyme. Once that chemical transformation is done, and in this case it could be a decomposition of a certain product, those products are then released by the enzyme. So you can see that the enzyme is there at the beginning and it's there at the end, so it's a catalyst. It doesn't get used up by this chemical reaction. Now, what role do metals play? How can they aid this? Well, a nucleophile on the enzyme can form a coordinate covalent bond with the metal. It attaches the metal there, and then the metal becomes basically at the center of the active site of that enzyme. When the substrate comes in, most often what happens is it attaches itself to the metal and then undergoes a subsequent chemical transformation. Now, in proteins, what can attach to the metal? We would ordinarily consider this to be a coordinate covalent bond, so we need to have a nucleophile. We know that there are amides in the protein backbone, in the polypeptide chain. Those amides contain nitrogen. The nitrogen, however, makes hydrogen bonds and creates the secondary structure. It really does not attach to metals to assist the protein. The attachment to the metals has to come from the side chains on the residues that are attached to that. So let's take a look at a few of those. So here we have the polypeptide chain represented in abstract on the left, and the R is the part that we're concerned with. So here are several examples of that side chain for the residues, including serine, threonine, asparagine, glutamine, histidine, aspartic acid, and glutamic acid. In each of these cases, I've indicated what part of those side chains can can be a nucleophile and therefore form a coordinate covalent bond to a metal. I'll point out histidine because we'll see an example of that later. It's the one example in these cases where nitrogen is the thing that is the nucleophile, and we know that nitrogen is a great nucleophile, and so it forms very good coordinate covalent bonds. This is particularly true for histidine. So let's look at an example. This is carbonic anhydrase, and it helps to convert carbon dioxide into bicarbonate ion. So here is a molecular structure of it, and you can see a little bit of an alpha helix on the right-hand side. There's also a little bit of one up at the top. Most of it, though, is like beta sheets that are colored in green and a couple of them in yellow. This also shows you the zinc active site in the carbonic anhydrase. Now, the way that zinc attaches to the protein is through a histidine residue. So we have a polypeptide chain, and you can imagine that it goes on and on and on for many, many, many atoms. And occasionally there is a histidine that sticks off as the side chain from this polypeptide chain. Now what happens is those histidines can bond to the zinc through that nitrogen. So in this case, in the particular case of carbonic anhydrase, at the zinc site, we have 3 different histidines that are coming off of different parts of the protein chain, and they help to form a tetrahedral complex with the zinc. The 4th site on that complex is initially occupied by OH, but this is in fact where the carbon dioxide is going to attach. The carbon dioxide will replace the OH. While it is attached to the zinc, it will be converted to the bicarbonate ion and then released after it's done. So the zinc site in the protein located right there, this is where it all happens. Now another example of metals in biological systems involves transport, and in particular hemoglobin, which transports oxygen to our cells. So here is a picture of a portion of hemoglobin, and there are several heme groups in here, and they're all pointed out on here. There are 4 different heme groups on each hemoglobin. And these heme groups are made up of a large polycyclic ligand. It actually is a polydentate ligand that attaches to the iron. Here's a picture of that heme group attached to an iron in the middle. We can see that there are 4 different nitrogens on that heme group that can form ligands to the nitrogen. So we can occupy 4 different sites on the iron, 4 different sites on the iron that attach it to this heme group. Also, we can have iron that attaches to the protein via a histidine residue, which is shown over here on the lower left. Globin is the protein that is part of hemoglobin. This histidine residue, which is part of that protein residue, attaches to the backside of the iron, which is now attached to 4 of the nitrogens on the heme group. So in this way, iron is actually the thing that accomplishes the connection of the heme group to the protein. It's not attached in any other way. The heme group is entirely separate. But notice that this iron has 4 sites occupied. It actually has an additional site available. That available coordination site is what enables it to bind to oxygen. So it forms an octahedral complex, 4 ligands from the heme, 1 from the histidine residue, and 1 is going to form to the oxygen. And so here is a picture of this heme group, and oxygen is the red thing that's attached in the middle of that big glob. That's the oxygen that is attaching to the iron in the middle. In this case, iron is colored orange. You may see that in the center of that big glob that defines the heme group. And the histidine residue that attaches to the backside of that iron atom is also labeled here on this particular diagram. So all of this gives us an idea of how iron can participate in transporting this oxygen. The story about how it actually delivers oxygen is much more fascinating, but I don't have time for it here. However, this gives you an idea of how hemoglobin is structured and an idea of how iron accomplishes the task of first binding oxygen, and then later on it will release oxygen from that same site.